Last time we showed that strictly diagonal dominance was a sufficient condition for convergence of the Jacobi method. However, there are some cases that are not covered by strictly diagonal dominance but still converge, and also it proves helpful to have a different method, should we say, that contrasts with the proof that we've already done, that also helps us compare the speed of convergence of two methods. And this method is called the spectral method, and that's what we're going to cover today. So last time we did a proof of convergence. We proved that a sufficient, I'm just introducing this word sufficient, by the way, I'll explain why in a minute, condition for convergence of Jacobi. Remember, Jacobi is xm plus 1 equals c minus b of x of n. Iterative method takes your vector into the solution. Is that A, your original matrix in A x equals B is C, is diagonally strictly diagonally dominant. Now this word sufficient has been introduced, that if you have a diagonally dominant matrix it will converge, but there are other cases, marginal cases should we call them, where A still does converge even though it's not strictly diagonally dominant by our criterion. So there are still other marginal cases, should we say, that converge. But don't satisfy the above. Now the classic case of this is this matrix here. So the 1 minus 2, 1 terms are common in boundary value problems. See the ODE section of this module. So this is not just a rare matrix, it's very common in fact. But what we find is if we look at the second row, so we see that the diagonal element, instead of being greater than the sum of the off diagonal elements, is just equal to the sum of the diagonal elements. So it's not strictly diagonal dominant, so it doesn't converge according to this criterion we showed. I mean, row 1 is okay, 2 is greater than 1, and row 3 is okay, but row 2 is not. So how do we analyze these matrices? Well, there's two options. One is carry on in the vein of method of norms that we've done previously. I've taken the norm, but also introducing ideas such as irreducibility. I'm not going to define this because we're not going down this method. I'm just trying to show you that there is a route, and I decided, and all previous module leaders of this decided that it's way too above the level of this module, and it's probably might be above the level of the degree really. It's but I just wanted to show that there is a pathway, and if you do a search for irreducibility and Jacobi, you will find papers out there where they prove this marginal case. But actually, there's a practical way. Use the eigenvalues of the B matrix, and this is going to be called the spectral method. And if you see, it's quite a common coursework to set spectral method. Yeah, and it will involve computing the eigenvalues of the B matrix. And that's something which is relatively easy to compute, whereas this starts to get quite abstract and difficult, yeah, almost verging on sort of the boundary between pure and applied mathematics at research level now. So let's pursue the line of this spectral method. That's what I'm going to do today. So the spectrum. So recall the error vector evolution equation. So we derived before, which is the error vector. Remember, the error is just simply the numerical minus the true solution. And the reason the B matrix is so central to this problem is because the error evolves under the B matrix. So we have that equation, and we use that in our proof by taking the norms. So that the method of norms involved in taking the norms, if I just indicate here, putting the vertical bars either side of here, taking the norm of your error and then proceeding down that line. What we're going to do instead is we're going to expand, or split up if you like, the En in terms of its eigenvectors. So there is a bit of theory behind why you can do this and the conditions on B to make a fair expansion or orthogonality of eigenvectors. Again, it's beyond this module, but I'm happy if anyone wants to contact me to point them to the little bit of theory that applies to making this possible. So I'm going to just assume that we can expand error as in terms of its eigenvectors. So we're going to call it so what are its eigenvectors? Well, let's define so the eigenvectors are B. I'm going to actually do the eigenvectors of minus B. It turns out to be, we're going to call them VI, and we're also going to make them normal. Also normal. What do I mean by normal? They have unit length. So i.e. the norm, we're not going to need to specify which yet. The norm of VI equals 1. Okay. So that's the L2 norm really. So the definition of your eigenvector, remember, if you take your matrix, multiply it by an eigenvector, it conserves the direction of the vector, but just simply multiplies through by eigenvalue. Okay, and we're assuming the eigenvalues in this case are real. So let's expand E0, our initial initial error, in terms of your eigenvectors VI's. So doing that, we have our initial error is C1 V1 plus C2 V2 plus, and I'm assuming there's big J eigenvectors. So C1, C2 are just constants that are used to construct the initial error. So if you don't need to know what it is, but if you imagine you had an initial error, these C1s would project differently on different eigenvectors, and there are J eigenvectors. So if we multiply by minus b, we then have minus b e naught equals minus c1 b v1 plus minus c2 b v2 minus cj b bj. Okay, so you pre-multiply by the matrix, and you can see where we're going. Because we've defined these as eigenvectors now, this simplifies massively. This will just go to a lambda 1 times v1. So we can know two things from there. Our E1 equals minus B E naught from error evolution equation. So the minus B E naught goes to E1. Yeah. And minus B E naught becomes E1. And because we've got multiplying by eigenvalues, we've got wherever we multiply through by b, we now end up with lambdas. So the error is now expressed as a spectrum of eigenvalues. Hence the word spectral theorem. Okay, we're splitting it up into a spectrum of the word comes a range of values, and then we're going to make inferences about that. So basically, if we just iterate this equation n times, so this process of multiplying through brings down an extra multiplication by lambda. So if we iterate and iterate, we end up with this general form. So we iterate n times, we have our nth error vector is c1 lambda 1 to the n b1, c2 lambda 2 to the n b2 plus cj lambda j to the n bj. Now, of course, we're interested in the error going to 0, but the robust way to pose that, as before, is to use norms. So we now we don't need to specify norm of En. So if we have the norm of En, and we know now these eigenvectors, we've set them up to be unit length. So these, when we take the norm of these guys, we know that the norm of any of the VI's is just equal to 1. So those just go to 1. So we simplify things even further by just having the constants times the powers of the eigenvalues. Sorry, that was a power. Let me reverse that. Got the 2 and the n in the wrong way. Plus Cj lambda j to the n. Okay. Let me write this at the top of the line again. Just copy it, and we can comment on it. Equals C1 lambda 1 to the n plus C2 lambda 2 to the n plus Cj lambda j to the n. So for convergence, we require the norm of the error go to 0 as n tends to infinity. Yeah. So that implies all lambda i's I missed out one key thing actually. Because you're taking the norm, actually we can put the absolute value here as well. So that's the extra bit that I missed out from the previous line. But because we're taking the norm, the absolute error, we can also take the absolute value. So all the absolute values of lambda I need to be less than 0. Yeah. So it tends to 0. So that's the first thing. The second thing is that the rate of convergence if it does converge, if this condition of maximum of the lambda I will be controlled by the maximum absolute value of lambda I. You see that? I mean, so e.g., just imagine you had e.g. if lambda 1, just for argument purposes, was 0.8 say, and lambda 2 was 0.4, then as you take powers of this, the larger eigenvalue is going to dominate. So by the similar argument for the whole sequence, it's going to be, as n gets very large, it's going to be the largest value that's going to dominate. Your other bits are going to be small. And this is a very useful simplification because it allows us just to focus on one eigenvalue, and that's the maximum of that absolute. So we can just focus on one eigenvalue. It's this one. It's the maximum of the absolute eigenvalues, which is going to control convergence, and that's got a name. S. S is the spectral radius. Reason being is because if you imagine you've got a whole bunch of eigenvalues, you've got the maximum one kind of defines a, an outer bounds on your eigenvalue spectrum, hence the word spectral radius. Okay, so it's not not using that directly geometrically, but it's you can see where the term radius comes from, and that's very useful because that's relatively easy to compute. If you've got your B matrix, so remember, lambda i's are your eigenvalues of B. So once you have B, you can complete your eigenvalues, take their absolute values, convert to spectral radius. Let's write it up again because it's so important. S is max absolute value of your eigenvalues. And next time we'll do a little example of this with a 2 by 2 matrix. It's all been a bit theoretical, today, but next time we'll do a look at a 2x2 example. Let me just make a few more comments. So now we have a spectral radius, we can say if S is less than 1, because if it's the maximum absolute eigenvalue, then the method will converge, whether it's Jacobi or Gauss-Seidel. So that's the first thing. You need S less than 1 to ensure convergence. And the smaller S is, the faster the method will converge. Past the error will go to 0. Yep. So therefore this allows us to compare Gauss-Seidel and Jacobi. So if S is less than for S for Gauss-Seidel is less than the S for Jacobi, that means we can prove with the spectral radius here that Gauss-Seidel converges faster. And I'll stop there and continue with the 2x2 matrix example next time. Okay, bye for now.